In today's video, we're going to talk about sizing ductwork, and we're going to talk about these topics here. First is the standard friction loss that is used when designing HVAC ductwork. Then we'll go into explaining what the friction loss really is. Then we're going to talk about some of the tools that are used to sizing ductwork, which is the ductilator, as well as some other duct sizing tools and applications that you can download on your phone. The losses in the supply and return openings should also be considered when trying to determine the full pressure loss in the HVAC system. And then we're going to talk about the fan and system curves, which will put together the system losses and the fan losses together to see basically where the equilibrium point is, and that is the operating point of the system. And we're going to go over this in this video. So this is what a ductilator is right here. This is a common one that's used from Trane, but there's others that are available. On the top here, you see there's the CFM, and the CFMs are listed here. So here is 30, and it increases this way, and here you'll see the maximum here is 100,000 CFM. And here is the friction loss, or the head loss, per 100 feet of duct. And these numbers are in units of inches of water column friction head loss. So if you look here, this is 0.1 inches of water column per 100 feet of duct. And also you see here, these are all in inches of water column per 100 feet of duct. If you look down here, this is the equivalent round duct diameter, again in inches, and on this side is the airflow CFM and the velocity here in feet per minute, FPM. And you generally want to size the duct so the feet per minute do not exceed roughly somewhere in between these two numbers. So generally for residential, you want to keep the NC level at about 30, no more than 30. So 30 falls right in between these two numbers here, the 35 and 25, which should fall somewhere in between the 1500 and the 1000. So around 1250, about, you'll probably get a NC that is about 30. So you don't want to exceed a 1250 or so feet per minute if possible. And this is the section of the ductilator that you can use to determine the feet per minute. And if you look down here, these are the sizes that you can select for all those conditions here. So these three conditions can be met with the duct sizes that are indicated here. When designing the HVAC system ductwork, the standard friction loss that we use is the 0.08 inch water column per 100 feet of duct, which is represented by this line right here in between the 0.05 and the 0.1. This is 0.08 inches of water column per 100 feet. Some companies may use a slightly different number, and depending on some HVAC systems, you may have to design it under a higher friction loss per 100 feet of length. But generally, the standard size that is used is the 0.08 inches of water column per 100 feet of duct. So there's a SI units, which stands for the System International Units, which is basically the metric system. The units can be in meters and things such as liters. In the US, what we use is the IP units, which stands for the imperial units, and these are basically units that can be in inches, feet, GPM. These are the units that are used in the US, so we need to follow that for this company. Because of that, I use the IP units here for the ductulator, although they also have the SI units for the ductulator as well. So if you look here, this is the ductulator, and on the other side you'll see that it's the SI units, but for our company and in the US what we use is the SI unit. So I'm going to demonstrate everything using this side. Okay, in the example we're going to go over, the CFM will be the 2000, and the ceiling height is going to be a small ceiling, so it's going to be about, let's say, 14 inches or so. So we want to keep the duct with a few inches extra of clearance just in case. So we're going to size the duct height at 12 inches or less. The NC level, we're going to have to keep it less than 30, which means that the feet per minute is going to be 1,250 or less. So between these two numbers here. So to do this, we're going to have to rotate this ductulator this way so that the 0.08 inches of water column per 100 feet lines up with this 2000 here. And we're going to measure a few sizes of the rectangular ductwork in inches using this bottom portion of the ductwork. The train has the two sides. One is the SI units, the other is the IP, so we're going to use the IP since we're in the US. So as I rotate this ductulator this way to get the 0.08 to line up with the 2000, this is what I'm going to do. So I look at the units for the US, which is the IP, and then I just rotate it this way until the 0.08 lines up with the 2000. So that's what I did, and these are the values at that point of 0.08 lining up with the 2000. So for that, we can use a size of 19 inches for the duct here. But in general, you want to keep it all even if possible. So we're just going to round that up to a 20-inch diameter duct. So, you know, one size we can use is a 20-inch diameter. But in this case, since we need to keep the height of the duct less than 12 inches or equal, this one we can't use. And looking on the bottom, we can start with the highest size we could use, which is the 12. And for 12, you can see the numbers are increasing in this direction here, and the opposite direction for the top numbers. So these numbers increase in this way, these numbers increase this way. So for a size of 12, we can use a size of about 26 inches. And again, you want to keep everything even, the numbers. So we're going to use the 12 by 26. So the 26 by 12 is one size we could use. And the standard is the first number represents the size of the duct in this direction here. And this is the plan view, so looking down on the duct. And the second number represents the height of the duct. So that's into or out of the page is the second number, which is the height. If this is the plan view that you're looking at, which basically just represents that you're looking at the duct from the top down. So the next size we can use would be a 10 by, I would say this looks to be around 34. So the next size is a 34 by 10. And again, keeping all the numbers even. If possible, you can also use odd numbers, but we generally try to avoid odd numbers just as a standard, unless it's required that we have to use that odd number dimension. Another one we can use would be the 8 by, this looks to be about 45, so we want to use a even number, so we're just going to use the next highest even number, so 46. So it's an 8 by 46 that we will be using. And another thing is to keep the ratio no more than 4:1. And what I mean by this is the ratio of the higher size dimension to the lower size dimension, so in this case it's a 26/12, should be no more than the 4. So in this case it's about a 2. So since 2 is less than 4, we're good. For this case, it's going to be 34/10. And again, that is going to be about, that's 3.4 here. So 3.4 is less than the 4. But in this case, the 46/8 is going to give us a number that is about, and this one is going to give us a ratio that is 5.75, which is more than the maximum ratio of 4. So this one we can't use. And this is again just a general standard that our company uses. If we really need to use a ratio that's higher than this 4:1, we can do that, but we generally try to avoid that. And that means that these are the two available sizes that we can use for the ductwork that is carrying this 2000 CFM, with the maximum height being 12 inches. Alright, so the app that you can download that I feel is a good app is this HVAC duct sizer. Alright, that you can download. I have an Android phone, but I believe this is also available for the Apple as well. So you can just download this app on either the Apple or the Android phone. Okay, so for this example, we're gonna have the 2000. So I typed it in this field up here, 2000. And the friction loss, again, you could type in the 0.08 inches of water column, which is similar to water gauge in this case, per 100 feet. So I'm going to set that to 0.08, which is the standard friction loss. And based on the aspect ratio, as we slide this up and down, the aspect ratio being the maximum 4, which is the standard we use. And again, the aspect ratio can go higher than this, but generally we want to keep it 4 or less. So a maximum of 4. And we're going to see the different sizes available. So as you change the aspect ratio, if you look on top, you'll see the duct height and width changing. So we're going to start off with the highest one, which is 4. I'm just going to type it in. And the duct height is 9 by about 36 rounded up. So trying to keep it an even number, I'm just going to call it a 10 by 36 as one size. And just to check, the inches are again 0.08 and the velocity is 1068. So less than the 1250 that we generally want to keep it under. So going down this way, and when it actually hits a 10, I'm going to take down the dimension. So it's a 10 by 32. That'll be another size. Now I'm going to keep going down. And let's wait till we get to the highest point, which is 12. So at 12, it's about a 24. I'm just going to round it up to the next even number, 26. So 12 by 26. Okay, and let's go to the aspect ratio where it's a duct height of 8. So that's going to give me about this aspect ratio right here, 5.22. And that's an 8 by 41. I'll round it up to a 42. So this size is a 8 by 42. So these are the 4 sizes that we got. So using the HVAC duct sizer app, what I noticed was that as the aspect ratio goes above 41, the sizes become more different than using the ductilator. So in our example, we actually had these sizes here. So for the ductilator, we had one size being 26 by 12. The other size was 34 by 10. And the other one was 46 by 8. And this is the one we couldn't use since the aspect ratio was more than 4, which you could tell by dividing 46 by 8. It's more than 4 there. Now, the sizes that we got with the HVAC duct size application is a 26 by 12, a 32 by 10. We also got a 36 by 10, and we got a 42 by 8. So the aspect ratio was increasing in this direction here. And as you notice, as it increases above 4, which is this one here, the difference in size was 4 inches. So here it was 46 and here it's 42. So that was a big difference here. For the lower aspect ratios, the size difference were pretty similar. This 32 is very close to this one, and this 36 is also close to this one. So this 34 is actually the average between these two numbers here. Now when the aspect ratio is close to a 2, so as the aspect ratio is low, here you can see that there was really no difference between the app and the ductilator values that were obtained. So using the app, I would recommend not going to anything over a 4 aspect ratio. But if you do exceed the 4, to not exceed it by much, maybe somewhere between 4 to 6. And if you are within this aspect ratio range, to increase the duct sizes by at least 4 inches in one of the dimensions. So this is something that I think should be applied when using the HVAC duct sizer app. Alright, now what we discussed before using the ductilator is the friction loss per 100 feet of ducts. Now there's different type of fittings that you can get for ducts. You can get, rather than just a straight piece of duct, you can get radius elbows such as here. As you can tell, they are curving this way. And you can also have 45-degree connections such as this here, which is also represented here in this picture. Or you can have duct connections that are just directly 90 degrees into the duct, as in this case. Or you could have duct taps that are just 90 degrees into something and circular or rectangular. Now this up here is a 90-degree duct elbow with turning vanes, and turning vanes are these things here, which you can also see in this picture and also in this picture as well. So turning vanes are used to reduce the friction losses across this elbow. Now to figure out what the friction losses are for these connections, you can use tables such as this, and I'm going to go through one example of how all of this can be applied. So this distance here is D It's kind of hard to read here, but this is the D distance, and this is the W, and here is the radius of curvature. So the larger the radius, it's not a sharp bend. So the smaller the radius of curvature, the sharper the bend appears. Okay, so that's what the radius is of this curvature piece. So based on the ratios, you get different LD ratios here. So let's say the width and the depth is 12 and 12. So here this is 12 in this direction, and the W here is 12. Then this ratio would be a 1. And for this example, let's assume the RD ratio is a 1.25. That means that this LD ratio is equal to 7. So what does this mean? I'm going to use an example. Okay, let's say in this example the width is 28 inches and the depth is 28 inches. And the radius of curvature is a 1.25, which means that the R over D, D being 28 inches, is 1.25, which means that the radius is going to equal 35 inches. So this distance from this center point of this curvature to this midsection of this duct will be 35 inches. And that's going to give us the LD ratio of 7. So the LD ratio equal to 7 means that the L is equal to 7 times the D. In this case, the D was 28 inches. So then the L is equal to 196 inches, or divide that by 12 to get 16.3 feet. So that is basically the equivalent length of duct for that radius of curvature. It's 16.3. So what this means is if you're creating a friction loss of duct, so let's say the duct goes this way, it curves, and then it goes down this way. When we size the duct at 0.08 inches per water column for 100 feet, you have to add up the total feet, right, that ratio is applied to. So you have to add the distance. So let's say this distance of straight run was 10 feet. And this also, let's say, is 10 feet. You have to add this piece of duct here. And if the equivalent size, which is what we calculated, was 16.3, I'm just going to round it up to 17. This is the equivalent of that 17 feet of straight duct. So when you calculate the total friction loss across this whole thing, you have to apply it to a distance of 20, which is this, plus the 17. So that's going to be 20 plus the 17, so you're going to get 37. So when you apply the total friction loss, it's going to be the 0.08 water column per 100 feet of duct. You multiply that by the 37 feet, and that's going to give you a total of 0.03 inches of pressure loss in this case. And there's other charts available too. Some of these charts just give you the equivalent length of straight duct in feet. So in this case, it's for round elbows. and depending on the pieces here, so in this case it's not very smooth. It's in 5 pieces. You can have 3 pieces as well as different degrees. So this is a 45-degree elbow, and this one would be a 90-degree elbow. Or you can have smooth curvature such as this, or a smooth 45-degree curvature such as this. And depending on the ratios, again, between the radius and D, in this case, and the elbow diameter, you can get an equivalent straight feet of duct from this table here.